Okay, we can continue. So just to wrap up on the main issues, the main remaining issues, there was this thing about the ensemble. So which are the best platforms to do ensemble? And I mentioned the H2O, and then current ensemble. I don't use it, but it exists. Then there's MLR. This is a bit more German project, but it's very good. And then you have the super learner at Subsample. If you look at the MLR project, so let me look at that. MLR is machine learning at R, nothing special, but what's special about the project is that there's lots of young people involved, and it's a really long list of developers, you see? Long list of developers, and these are the people that work in academia, so they use this academic time. I mean, they're paid by people, by government, to do science, and the way they do science is they develop stuff for R. And I think it's going really good. This MLR, I think it's going really good. So they have also very intelligent ways to do ensemble, and also the spatial cross-validation implemented, and you can incorporate coordinates in the modeling. There's already arguments which take coordinates. So I think it's very well done. So if you need like a general direction where to go, I would say, even though you could also look at the H2O, it's also very good platform to develop, but I would advise you to look MLR and Super Learner. These are the two frameworks for ensemble that I advise to use. That's at least what I use. So when you look at this when you look at the set of the available models in MLR, I mean, there's just 59 for regression, and there's 82 for classification, 12 survival analysis, 10 for cluster analysis, and some multi-label classification. See, there's lots of models. I mean, it's about 150 or something. So 150 learners. Well, for regression, okay, you have 59. So how do you do this then? I mean, do you take all 59 and you test them with your data? Would you do that? Does it make sense to take all 59 and test them on your data? Why?
You could select a kernel-based method and then a tree-based method and then a probabilistic and start testing the different families of machine learning.
Well, so that's what Madeleine paper, the paper I sent from Madeleine, it's about doing that. Let's test a lot of models on a large stacks of data. And she did so that, okay, some models for soil data, for predictive soil mapping, they come up, usually they come up on top. And so when you see that in a couple of studies, that you see that some models are always behind, lagging, there's no need to retest it. But if you have resources, you don't have to take all 100% of your data. You can also just make a code that takes a subset of your data, so it's computationally fast. And then you just want to quickly see what are the differences and how big are the differences in accuracy. So you just quickly, and then you subset, and you say from this 59, I only have like 5 kind of always outperform, and they kind of, that little cloud outside of the others. And then you say, then I do ensemble on these 5. That's what I would recommend anyway. But technically speaking, yes, because of this MLR framework, it's just a few lines of code to say, okay, make me ensemble out of 59. It's possible. The object will be then even much bigger, and it will be computationally also probably 50 times more computationally intensive. But it's a few lines of code. Okay, what we're going to do now, we're doing practical. So where I'm going now is the this one, so if you go to my GeoMLA repository, now you have to follow me if you want to be able to run this buffer distances and random forest on spatial distances. You have to follow me, right? So you have to go to this URL, which is my home, so not Environmetrics, but my home, because I made that before we got the GitHub from Environmetrics. So there's a GeoMLA. GeoMLA is machine learning algorithms for geographical data, GeoMLA. We even had a conference, GeoMLA, a couple of years ago. So if you go to this GeoMLA, then you have to go to RF uncertainty. And then there are different codes. There's the RMD, R Markdown, Markdown MD, and R. So we're going to use this, basically the RMD file, I think I will look at. But because I need some data also from that repository, the best thing is to download the whole thing. So you say download zip file. You download it, and then you put it in some folder. You uncompress it, and then you get a local copy of that GitHub. And now it's local on this computer. And then I will clean up here all these things I was doing. I don't need it. I will clean up and restart my R. So now I have a clean session, and now I can open. I do open file. And now you look at this folder, RF uncertainty, random forest uncertainty. I'm doing this on purpose because Herod is also going to focus on basically uncertainty with machine learning. And I open this RMD file. Can you see from the back? So you see this file now has the text. It has a text, but it has also R code. It has instructions how to do things. So for example, I can install Ranger. You can install it from GitHub. I usually now install from GitHub things because I want the most recent version. Although it can be it could have a bug. Sometimes it's not a good idea. 90% of cases is the best idea installed from GitHub. So you can install that. That can take time. So and then if you install everything, then it should all run. So getting all the packages loading. If you get an error message, it says the package is missing. Then you have to do install packages, right? Install packages, and then you install the package you miss. I have some legend here. This was a bit old-fashioned. I made a legend by hand. Yeah. Yes. But and then I load the data. If I do this demo, so you see all this data appears here. I just do demo mass, and then I say echo is false. So don't echo, don't show me what you're doing, just load it. And then I get this data. I have this mass grid, mass points. There's some, I think this is some polygon and line. This is, as I said, this is a classical data set from the GStat and SP package. And you see it all around. If you want to develop something new, you have to, and it's geostatistics, you have to do it with the mass data. And then one day, you have to take a bicycle and go to that place and do the pilgrimage, the geostatistical pilgrimage, or hiking there. Timo, have you been there? Do you know the area? No. It's a towards Maastricht. It's Limburg. It's nice. It's nice place. It's like rural. It's nice. It's good, nice for cycling. Okay, so I load this data, and you see this data now. You see this two dots means go one directory up, and then inside the RF versus Kriging, there's a data mass folder, and here I load local data, which is not available in the mass. It's not available in the mass package because it's from the Global Surface Water, the JRC project. I think it's a very nice new data set. It didn't exist when the mass data set was made. Have you heard of it, Global Surface Water Probability? So they took 30 years of Landsat data, and they calculate the probability of pixel being a water body. And so imagine if you had a flood events, and if you had times in the past where there was, pixels with wetlands, then they will be visible.
So can we just check how many of the people can actually do what you're doing? Is everybody?
No, we will go step by step, and then I will show you. Yes, but it's very good if you can follow. By the way, I customize a bit RStudio. So one of the things I do, for example, I put this soft wrap. You see, I put the soft wrap, so all my text is in the window. The other thing I do also, I put line numbers. It's a good idea to put line numbers, because if you ask me, hey, I'm having a problem on line 74, then we look. And the other good thing to do is I also show the white space characters. So you see, you have, if it's a space, I can see it's a space. So anyway, that's what I do, because I'm also a bit geek, I need to see geeky stuff. Okay, so that's the thing I loaded. So basically, I just added 2 more layers. So now when I look at this mass grid structure, and then you see I added these 2 layers. Maybe I can plot it, so you just see how it looks like. SP plot. You can plot now the SP objects many ways. Maybe the SP plot is not the best way. So I get something like this. So you see, this part here was being flooded. This amazing data set. I mean, this 30 years of cloud-free water coverage, right? And it's for the whole world, and it was made on together with JRC and Google team on Google's infrastructure, Google Earth Engine. When you go to EGU, you see these projects. I mean, when they're massive and they make something significant. So I added that because I think maybe that could help with mapping the nutrients. If you know that, like, they discovered that these nutrients these metals. So the metals in soil, they discovered that they are caused by flooding effects. And so as you get closer to river, you have a higher values, because maybe there was some factory or industry that used to release wastewater, and this wastewater had a lot of these metals, and then once it floods, it goes in the soil. And that's why it's important to have that estimate of the flooding probability. So I produce that, and then I combine this data. Sorry, I didn't load this one. This data now I combine into a regression matrix. So I have something like this. Don't get scared. What do you see here? So you have these are the original data from us. This part A, part B. Soil type, flooding frequency, but this is kind of manually drawn flooding frequency. Then this is the elevation from the national elevation data set. And this is the LGN, is the national land cover data set. And then this land cover data set I just converted to indicators. Do you see this? It's a very elegant way here with the model matrix function. You can convert a factor into indicators. Sorry? Yeah, and then you get these dummy variables. Yeah, maybe dummy is not a nice word. I don't know, dummy variables. Indicators. I mean, our papers can be maybe dummy, but I don't think the like indicators are dummy.
But that's a common name.
Yes, it's English language. I don't know. English. So okay, and now we do this buffer distances. This a bit, you know, it takes a bit of time. It's 155 maps, and it will pile up on my RAM. If I look at my RAM, I mean it goes up. This is the CPU memory. So it went a bit up. I have here 6 gigabytes, so it's fine. But it creates 155 maps. And I can plot. Let's plot few maps. Once we plot this, I mean, I think then it will become for you clear what is this distance. Many people ask me, well, what are these distances? What is that? Well, you know, it's just each point, and you have a distance from that point to the rest of the space. And these are these trivial buffer distances. If I had more time to compute, I will calculate like this. So the watershed distances, upslope and downslope distances, and also these terrain complexity distances, right? So it's 155 maps. I mean, I could plot also a bit more, you know, so you can see how it goes from point to point. But I could also just, let me put just randomly now. I need to put random numbers, let's see. Multiply by 100. So I put maybe 8 maps. It's getting a bit abstract, this, what I'm doing now here. Do you know this function? How do you pronounce it? No. There's a whole blog teaching people how to pronounce RUnif, a random uniform distribution. But many will say RUnif. RUnif, but it's R uniform. So there's a blog that explains that you don't pronounce it like that. If you do it on some R conference, they will laugh at you. Let me see if I did everything right. So I simulate 8 random numbers from 1 to 100. That should work. Let's see. And so here I get 8 random points. And you can see these buffer distances. Okay? And then we make this formula. And this is a bit, it's a silly formula, right? When you look at it, it's really long. So it has, each of these distances is a covariate. So basically what I'm trying to say is that distance to single point explains variation at any pixel. So like every point can be like influential, right? And you do it together with covariates. And some of the covariates are these indicators. So it's all at once. And this is what I said when I was doing the regression kriging. There was always this frustration that we do separately regression and then variogram, you know, but it's separated. So you don't use variogram to estimate regression, and then you don't use regression to estimate variogram. But there were some approaches to do like by iteration. You do regression, then you do variogram, then you do again regression and again variogram. And then it kind of stabilizes. That's what they used to do in geostatistics. But many people don't do that. Anybody who used regression kriging never did that, right? Nobody did it. I don't think so. You do it? You've done it? What did you use to, how many iterations? 10. And then you stop. And is there a difference between first, second, third iteration? Yes? But little difference or big difference? Yes. Yes. But most of people don't. They would just like, regression, kriging, and sum up. And I like it now here because it's at once. And it's based on lots of bagging techniques, so lots of trial and error, and there's like a 500 models basically. Okay, next thing I do, I bind. So I have to bind now the buffer distances and the feature space covariates. So I have the feature space covariates, they represent kind of processes, and then you have the buffer distances, they represent geography. And so we have these two types. And then we can fit a model. And now I use Ranger. It's a funny name, Ranger. I asked Marvin, why did you call it Ranger? But it's a very good package. It's Marvin has been really updating it. He has a very active discussion list on GitHub. And I also told him some things. I wanted the quantile regression, random forest, and he implemented it. He says, let me look at that. He would just look at the literature. He makes it, and the package is in C++, so it's scalable automatically. So it's optimized for serious projects. And this is also a backbone of Open Landmap. It's, for example, Ranger package. If I didn't have that package, it will be difficult to make all the maps.
So what was his answer when you asked him?
Ranger, I think, because he says, random forest, there's already a couple of packages in R. So he didn't want to call it some random forest something. And he saw that Ranger was free, so.
Okay.
Anyway. But yeah, but it's a bit like you go, hey, what is Ranger? I would think like there's some R package for the rangeland management or something. Okay, so we do that. That was very fast, scary. And now we see that model explains so it's 60 R squared 0.65. But this is just based on this bagging, so it's not a spatial cross-validation.
What is the R square if you do not include these distances to the observations?
Okay, let's do that. Have I done that somewhere in the code before?
It's not in the code.
Not here, okay. Yes. So what I need is I make another, so let's make it below here. I just copy this. I leave everything the same. I just put another model and I call it M0. And then this model, let's see where I make that. Yes, here I make this FM1. So I now make a FM0. Right, and then here I just remove this buffer distances. As far as I remember, it will be similar.
It runs in parallel automatically?
Yes.
The buffer distance?
Yes. Oh no, wait, I now replace it has to be FM0. Okay. And now I say the model is FM0. And, okay, I just have to reduce well, let's take it out, mtry. It will estimate it automatically.
Why did we get this error message?
Because of mtry cannot be bigger than number of covariates.
Okay.
It says here, cannot be larger than number of variables. And then it stops. Because it will try to estimate it, but it doesn't fine tune it. It just takes a rule of thumb, which is a square root of number of covariates.
Right.
Yeah. Right. But you could fine tune the mtry. That's
Why
what.
Did you put 22?
Because I did fine tune it. I just didn't want in code because the fine tuning is very computational. So I already fine-tuned it, and I knew it's 22. And then I just put it because this is a code just to think about uncertainty, right?
But you were discussing that before about this fine-tuning, but the fine-tuning is based on the data that you use also to later on compute the out-of-bag. So actually, it's maybe you get too optimistic results in that way by calibrating these meta parameters.
Oh no! There's a package to do just random forest fine-tuning.
Yeah, it's just that you don't want to use data for evaluation how well you
No.
that you already used for calibrating.
No, it doesn't. No, it's really properly done. So
Okay.
so it always takes out the data which is used validation and training is different always, also for fine-tuning. And so it's well done, but it's computational,
Okay.
and it has to fine-tune a grid of parameters because there are 3 parameters in a random forest. So you cannot just say I want M try. I mean, you could say, but it's not correct. You know, you have to find that grid of all combinations, and that's why it's computational, because you have to look at all that grid, and then you find which combination.
That really doesn't exhaust this search.
Yes. Okay, so you see this one is 56, and the other was 65. So it's a 10%. Yes. Yes. Yes, it's running. Thank you.
Because it's going too fast, or what?
Yeah. We will put the video on the YouTube channel, and you can come back and watch. I mean, I will cut out. It's boring if it's like all these things that I'm just chatting. I usually cut out. I just leave the coding, you know, just the hardcore coding. When I talk about my scientific problems, I cut out. Also, if I insult someone, you know, I want to cut it out in science or in politics. Oh yeah, but look, you know, most important thing is the book has all these examples, and book has also text explaining, and there on GitHub there are tutorials. So nothing is inaccessible. Everything is for you. You just maybe need some time to go and look at things. Yes, so I can compare the 2 models. Oh no, what do you want to look at? Sorry. FM0. So it's just this. So just the covariates, no distances. Well, I mean, it's funny. There is a distance to river. So actually, I should have taken this distance to river out also. Yes, because that's geography. And then compute. Let's just do that. I just take the distance to river. Now I will just copy paste and fix because I don't have time to make code for that. So let's see.
I mean, that is what it's supposed to be, right?
So take this. Sorry?
You do better.
Yes. Yeah. But a bit better. But let's say if we take the distance to the river also. Okay? And now we compute again. Much worse. Do you see this? It's big difference.
So Tom, if
yes.
you left distance to river out and just use your grids, I wonder if I'm not suggesting you do that, but it might give you everything you need without distance to river.
Let's try that. Excellent.
Let's add the points in again. The distance.
Yes, it will add. It will be again high. I don't have to run it, but it will be.
I would like to see.
You want to see it? I hate you. Okay. Okay. So where was it? FM1. Yes, because it explains the process. But let's try now without the distance and with. So let's do that one. So that was this. So I tried 1, 2. I hate this in when you do on GitHub. You know, you have to do the enters. It doesn't do soft wrapping GitHub. It's one of the biggest problems with GitHub, I think. No soft wrapping. Okay, so I take the distance out, and so now we have the buffer distances, but I promise it will be also high. Let's do, that's FM0. Yes, it's again like above 0.50, but it's not as good as when I do the whole thing, everything.
That is shows with the buffer distance.
Oh yeah, by the way, this R square, that's the stuff I told you I made a mistake because I blindly believe in this Ranger R square. And then I told Marvin I hated him. And then he says, no, it's you made the problem. You don't know what you're doing. So don't hate me. And he was right. His package is fine. He's, by the way, in medical research. And we discovered, I told him, like, when I called him, I said, look, I'm working on really big data. And I said, I'm working on the whole world, and I want to use your package. It's huge data. And then he said, okay, but how big is the data? I said, it's like a couple of terabytes. And he almost laughed. And then he said, look, we have like, 100 terabyte data sets. But they were working on genes, on genetical data. And I said, this is so funny. You work on something very, very small, and your data is like 10 times bigger than my global data. This is really funny, yeah. Anyway, so it was, I made a mistake. I was just blindly looking at this R square, but this is a spatial problem. It's a spatial problem, and so some cases, what happened, that this R square will trick you. You will think, oh, well, I get R square 0.85. Job done. I have 0.9, I don't know. But I got it because I use these 3D models where I had the points, the profiles on the same spatial location, so the covariates repeat. And then Ranger kind of didn't have problems when he did like a bagging or something. And he says, yeah, R square is high. And then I started doing spatial cross-validation, and I said, okay, realistically, I need to take the whole stations out, and the best is that I take actually whole blocks of points out, and then I do cross-validation, because that's the actual accuracy. If you then do a design-based sampling, and you force yourself to go like a simple random sample or something, and you collect the points, then this is the most likely accuracy that you will measure. Okay?
Can you run one more model, Tom?
Which one?
The one with only the buffer distances, but just selecting 5 or 6 buffer distances randomly. Can you do that?
Sure, yes, it's not a problem here.
You can say from 1 to 5.
Yes. No, it will be less if I will randomly pick up points. So I will tell you, it will, R square will drop if I take only like 5 points out of 155. The R square will proportionally drop.
But not the points.
But if I will take critical points, if I'll take like hotspots, then the R square will go high. Then I can only use like 10 points. Okay, but if I randomly pick up 5 points, I will again have a small.
But not points, the buffer distance.
The buffer distances. The buffer distance. No, sorry, buffer distance, not the point-based buffer distances. But if I will take the hotspots, then most likely, especially because the R square is also, it's fortunate, unfortunate. R square is related if you have a high values and low values. If you lose a point which is a high value, that in absolute terms it causes error to go much higher. If you lose some points with a low value, your R square, it's like the errors are smaller. If you miss predicting small values, your errors will in average be smaller. So that's why in many models, like the map I showed you with Ensemble Spatial, so where I have the high hotspots, high value, and it's isolated, that's where my highest error will be. Okay. I go further with the model. So now this is also very, very interesting. Look at this. We can now sort. Ranger has a functionality to also quantify the importance of each specific covariate. And now we have this mixture of feature space and geographical space. And we see that the point number 54, it has high influence. Point 54, 55. So which are these points? So I will have to go and plot it and stuff, I don't know. But I know these are these points which have high values.
You do that easily because you did that are unique. You could just put 54 and 55.
Okay, I hate you.
Well, yeah, fine. I don't want you to do all this prediction error and stuff and so on, because we do that this afternoon again, Tom.
Okay, okay,
So focus on this.
okay. Yeah, that's the high spot. That's the high spot.
Right.
Yes, these are these few points which have high values, and they come up as very important for the model. So, by the way, from which code should I stop here?
Well, not too much about this uncertainty.
Okay.
And
you know, I also
we'll do it later this afternoon again.
I do find this uncertainty is very important. So I don't mind if you repeat some stuff, because I think that's the best way that people also absorb it.
You're in charge.
Okay. But you tell me when I come to your codes.
Can I ask something else?
Sure.
So it says the points that have very high zinc values, they're really important covariates, the
Yes.
distance to those points. So, but this distance map is just the distance. It doesn't actually include the zinc concentration.
No.
So how does it know that this is a point with a very high value?
Importance, you mean? Importance.
Yeah, but is importance, you say importance related to actually an extreme value in the zinc, or not?
In this case, the importance comes from the bagging. So the bagging means you take some points out and in, and then it tries and then see some of variables if you make so they have a high impact of the values and the accuracy.
I was just wondering if you like making a scatter plot of the zinc concentration
Yes.
on the x-axis and the importance in the ranger.
Yes.
Is that a strong correlation?
Most likely it will be a strong correlation.
Yeah, and then I wonder why. Because I thought it's only about where they are and not what they are.
Yes. No, because that's what I just told you, is that if you have high values, then the errors will be higher. So maybe Ranger will have to have kind of conversion, so to penalize for the, I don't know. It's a you know, it's always like this tricky thing is, like, do you want to are you care about the absolute accuracy, or you care about the pattern? You know, sometimes you can get much nicer image of the pattern, so you see where the low and high values.
What it cares about is the absolute value.
It's just absolute value. Yes. Yes. It cares about the errors. Yes. So it's kind of it's like least squares. You know, like you want to minimize the errors.
I
Yes.
have sort of a similar question. I wondered how deep you have to go into the importance list before you start seeing attributes that are related to the process. I mean, like distance to river comes out right near the top, but what if there was topography like slope or wetness or something? I think it would be interesting to know if your model was just portraying the geographic relations, where there are all the layers there, or whether it's driven by process.
Yes, this is all modeling. Like data science doesn't really explain the processes. I mean, you know, it just looks for the patterns and relationships. And
if it was elevation driving it, and there was a hump in the middle of you showed us earlier how to.
And that's what if you remember the last lecture, what I told you. Now I realize that this post-model diagnostics, so partial correlation plots, and all these other things that you can do, then that's where it becomes important. And this is where the expert comes, right? Yeah. And you know, I was thinking machine learning is like, you know, you fit the model and predict it. And I was so wrong. It's just a little chunk of machine learning. Maybe 60% of machine learning is this post-model diagnostics. And I'm just doing now one, which is the importance. But then you do partial correlation plots. Then you do, you can pinpoint to individual points that have the most impact, you know, so there's all these diagnostics. And then you go with your knowledge. And then you find, as I showed you with the example with the bulk density, then you find, oh, we have a problem.
I guess I was just thinking, because in the old way, you saw your model before you did the spatial with the creating, right? You only create the residuals of after you saw the relationship amongst your attributes. Now it's all kind of blended in together.
Yes.
It'd be nice to sort of see it this way, separated out again, in that same way in the old way.
Partial correlation plots. You can still do a single model, but then you look at it like, so yes. Yes. Yes, Marcus? Well, so here this distance is like distinctly the most important, and you see the number, it's like 38, and then this number for the geographical distance is 9, so it's 38 to 9, so it's like 4 times more important. Obviously, the pattern of this zinc in this area, it mainly matches the pattern of the distance to river. That's obvious, okay? And in most of cases, when you have a real data, I would be really surprised if you will have this buffer distance to be the most important covariate. I would be really surprised. So the point here is to replace the grading part with this. Yes, if you want to formulate it like this, yes. Yes. Maybe not whether the term replace is the right, but to incorporate this spatial dependence between points into learning process. But if you don't have it, for example, if with your conventional covariate, you explain most of the variance that you have in the data, then you will not get much more with this approach. I mean, you have to have a spatial structure. Yes, you have to have it, yes. Yes, but the kriging is the same, if you don't have a spatial structure, you don't do kriging. And I did check for these maps, the ones I showed you, I did compare, you can, if you make these predictions, right, and you see it is spatially continuous, and you can fit a variogram, you can randomly sample points, and you fit a variogram, and you get about the same structure, except the nugget is lower. But you get the same structure as if you just take the target variable and fit well, it's a bit less because it's residual variation, but it's about the same structure, similar range, So it comes back in the predictions. So it is, makes it easier, right? So this is the best example, right? This is the best. So it makes it easier. You incorporate the distances, but it does chop off these points. You see these 2 points? They get chopped off. And now, yeah, we will so this paper, the PJ paper was exactly on that. When you make a paper, it's not about your opinion. It's about whether you do an objective comparison or not. So when we made that paper, we went and compared really actual accuracy and also accuracy of the uncertainty, right? You have this. I'm very proud of these plots. I think this is really the way to go. This plot here. So maybe I explained that that's something relevant. So for me, these 4 plots, it's what I can recommend you if you want to do predictive soil mapping or whatever. You should always make these 4 plots. One plot is the observed to predicted. It should be 1-to-1. If it oscillates, you have a problem. Then the second plot is this 2-dimensional plot, which is the accuracy and the accuracy of uncertainty. So this one is the accuracy, and this one is the accuracy of uncertainty. And perfect model is here in the center. Do you understand that? So it's model which has the best accuracy and also the prediction error. It has a standard deviation of 1. It means it's a perfect match. If you have a higher, then you're doing underestimation, so you're over pessimistic. If you do overestimation, then you're over optimistic. And then you can plot, and this is universal. So it doesn't matter the scale, which variable. You can do rainfall or soil carbon or whatever, and you can plot it because it's 0 to 1 scaled. And then you get a model comes, for example, here. So here it means accuracy not so good, but it's a realistic prediction of error. Or you get a model somewhere here. It means both model error and the accuracy not so good. And that's what we did for these models. And this is what came out. I can show you that. This is for the thick and the mass data set. So this is the RFSP, so it was a bit worse than the Kriging. It was a bit worse. But when we do for thick, and further, as the point data becomes bigger, the difference is smaller and smaller, and eventually then machine learning gets better. The machine learning does need to be efficient. It needs non-linear relationships, complex structures, complex relationships. Then it outperforms any linear models. But if it's close to linear relationship, then it could be that it's more efficient. Also because of Ensemble, you have to do the subsetting, so you never really use all the points for model building. But yeah, so that's what you got. And then you have the second plot is that's the second plot. The third plot is the QQ plot. And then the fourth plot is the variogram of the cross-validation residuals. And the best you plot them like this. The variogram of the cross-validation residuals. It should be a flat line. If it's not a flat line, you have a problem. It means if there's a spatial dependence, then it means you have a spatial bias in your model. So somewhere it will over-predict in one part of the area, under-predicts, another part over-predicts. But if it's a flat line, then the job is done. It means I have a balanced, a predictive soil model, and job is done. And these are the 4 plots that I recommend now to people. If you want to have something like in one page, you say, this is my model, and then you can put it, and you can put multiple variables. I'm going to put that in the landmap package, so it will be available. For now, I can do it, but I need to make it professional. So you would just fit an Ensemble model, and you will say plot accuracy or something. It will make these plots by default. So I'm working on it. If you want to help me, that would be great. If you help, you become a co-author of the package. So and it's going to be an awesome package. So better pile up because the time will expire. Okay. I'm back here at the code. I just wanted to do the map. Then I will stop with that. Quantiles. Where's my quantile? So something is missing here. I know what's missing. Something I jumped over.
The line where you define the quantiles.
Yes, quantiles. Oh. Yes, here, this one. I didn't define it. So what do I do here? I just define one standard deviation up and down. Right? This is one standard deviation, median, and one standard deviation up. This is how you can do it universally.
You assume normal distribution.
I assume normal distribution.
Or zinc.
Well, I assume now for anything. I'm interested. I assume that that it's, but it's quantiles. It can be when you have quantiles. So you don't have to have a normal.
No.
So you're just interested in this. So you're interested in something that can be skewed, but you're interested how would it match a standard normal distribution standard deviation.
So what you compute is 16 let's say, quantile, 50% quantile, the median, and
Yes.
84. And in case of a normal distribution, it would be plus or minus 1 standard deviation.
Yes. Yes. This is, by the way, what Gerard is going to explain you more in detail, but just to show the result of when you do prediction with Ranger and you say, I want to do the quantiles, then you get a matrix. So let's take a look at that matrix.
So, yeah, you will show that now, but so when we do this quantile regression forest, we predict quantiles and not like the mean. So maybe you can also, if you have time, do it without quantiles and just predict the mean, because it will be interesting also to compare the mean with the median. Tom, are you listening?
So I just do the without quantiles. But I
let's
yes.
see what happens.
Yes.
If
No.
you compare the mean with the median.
No, sure, yeah. Yeah. And by the way, I didn't listen. So I just remove this out. That's it.
Okay. As easy as that.
And so now I have this. By the way, when I do Ranger, it's a bit. So what you see here, it's not a spatial object. I mean, I do a prediction, but it's not a spatial object. How do I plot this? How do I get that now to see, what's the prediction on the end? So I need to copy these values. So let's do this. So I know that the data will match. So that was a zinc RF, and so now I just have to copy. It's just like this, nothing special. I copied it because it's exactly the same structure. I put it back in the raster, in the spatial grid data frame, and now I can plot. And then we should get. No, what did it do?
The window open? Or?
If it's the margin, probably plotted in the same, below the line, below the chart.
No, should have appeared here. Well, let's do it one more time. It's a spatial grid. Yeah, it got really stuck. Let me try SPplot. Yeah. So then you get this thing, right? And so that's the output of just a best prediction, so no quantiles, and using a combination of all this GRC, flat frequency, and distance to river, distance to all the points, and that's the map. It is, sometimes you go like, okay, this is okay, fine map, but I don't really see things, so I need to get that out of R. I need to get it to some GIS. So then I do so I'll just make a TIFF. Yes, I think this should work. Okay, I make the TIFF, and then I can open that in QGIS. Oh, which one? I guess here's one. What do you usually use to visualize things?
Map view works really good.
Map view also, yes. Map view can be used. So a quick way. Map view. So imagine this, I could do a plot, but I can do interactive plot. So you plot a map, but it's in leaflet. And you get it, poof, it's interactive now. Have you used the map view? And it's a bit transparent, so I can put also satellite image. Yeah, so I see the satellite image. I'm still in R, by the way. I didn't move out. But I can do the same thing in QGIS. I just drop this, and then I want to see satellite image in the back, so I need a plugin. I need some WMS. This one. This is a really highly used plugin. 1 million downloads. I think it's #1 plugin in QGIS. They should have put it as a part of QGIS. And so now we put let's see. No. Okay, I put all the plugins. And now I put, for example, Google Satellite. And you see it matches. Now I just have to set up some nice color ramp. Of course, we always use the rainbow color legend, right? They don't like this rainbow color legend. It's a lot. There's a lot of color legends in R. I mean, you can really play with it. So let's try this one. Voila. So now I have the red is the high values, blue is low values, and I probably need some transparency. Like this. Okay. So we can, if we zoom in, we can see also how big are the pixels. We can see that some pixels also fall in the water, so which is artifact. And then we would like to see there's another nice plugin, value tool, I think. Value tool. Right. So here's the value tool. So now if I move around, you see, I see the values. So I move around the pixels, I see the values. And we would like to see the points on top of it. So let's go points, right, OGR. I want a shapefile, right? If I do this, if I only do this, I hated this. It's always asking for this driver. It cannot recognize that it's S3 shapefile. If you're new to RStudio, you see I don't type everything. I do lots of with tab. So I type 3 letters and then tab. Very high chance it figures out what I want. So I write this one. Oh, it wants the layer too. A layer is this GIS thing. You can have a one object and have multiple layers, and like you can combine, for example, lines and polygons and stuff. So you just want one thing out of it. Okay. So now I have the points also. Again, I can drag and drop. So now we see the points. and I would just add the labels. And this was the zinc. And so now we have everything. So you see I can move now, I can move next to the point, and I can see the predicted is 1,500 something, and observed is 1,800. So this point is very close, this point is very close, but this one is a bit chopped off. There's a smoothing effect. How many of you use QGIS? One more time. Oh yeah, okay. So you know this. This thing. Have you used this WMS and value tool, and do you know these packages? You can easily get them. Plugins, you get them easily, so it goes very fast. Yes. No, it's you see much smaller. It predicts 1,000 something. Still, because you remember the distance to river is the most important. So because this point is still close to river. Okay, so it does stays, and here they're a bit higher values, right? Here all the values are like 200, and here you have the values like 700, and so it does everything around river stays higher. But yes, but it's still much less. I mean, this is 1,600, and predicted is 1,100. So it is much smaller than here.
So it's a value of which, what value?
Oh yeah, well, so there's like a classical questions, is it when they say, oh, is it an outlier? Well, outliers are no problem, outliers, but is it an artifact? Is it an error? That's the question, because error is a problem. There are errors in everything you do, there's a bit of error. There's no perfect data set, maybe. But the problem is if there's an error, somebody mixed wrong material, or they didn't use the right laboratory method, or so there's a gross error. So that's the question. Most likely, this is bit outlier. And so if we want to zoom in and really understand this, yes, I don't know, it's a bit of here floodplain also. So it could be that just this little thing was flooded, and could be that this point is just here in the forest, maybe a bit higher, and then the values are lower. So, also you have to understand landscape. I mean, do I have Earth Engine? Yeah, here. So let's go here to that place. Yeah, so I made this little package called PlotKML. And so you remember here I did a view, a map view, and then I got the map. I can also do this thing. Except I have to load it first. Yeah. So we can get that same map also in Google Earth. It's amazing this when it goes like slow. It's like aliens landing. So I can turn off this transparency. But what I want to show you now. So look at this area now. It's like I'm looking here, and let's look at a bit historic data. So this is amazing. I mean, this landscape changed so much, right? And so if you don't know when were the points sampled, you see this was water, all water. So you have to know when were the points sampled. Like this is 2007, and imagine if the points were sampled in that year, and if I see the point is in the water, then I know, okay, something's wrong here. But absolutely use Google Earth Engine. It has more and more of these historic images, and you can see that you can see how much landscape changes, land use. Like, look, for example, this here, it's a bit of like a pond, right? But if I go back here, it was a farm. The landscapes are changing so much, especially in the Netherlands. So anyway, so then you have to look and see whether you can do some interpretation and say, okay, I understand these values are like this because of that. I think, this, if you look at this river, there's a little spot where it kind of also slows down because it goes like this. And maybe because of this has to be also taken into account, where the river slows down a bit, or, maybe it floods more. This metals will be much higher on this side, because it meanders on this side, so the water is always flooding that way. So anyway, so these are all the packages. It's you see, it's a very nice in R now. The spatial community, they will develop a lot of things. So you want to have a web mapping view, you want to have a Google Earth view, you want to get data that you want to load. It's like there's lots of things available. Even in landmap, what I'm making now in landmap, it's a functionality to landmap. Yeah. So functionality, if you want to get global data, I'm making a little function which is called download landGIS. So it will download from this 1 terabyte. If you just want Switzerland or just want some little area, then it will download it. So I said I want the clay content. So it just gets the clay content. I mean, you have to estimate the bounding box and things, and then it will run a web coverage service, and it will just get that, and it's very fast, very efficient. So it will be like a spatial database query, and then you get the data, and then you can compare. So that's already available in landmap, but I have to make it even easier for people. Like if you want to crop, like I just want Switzerland.
Can you list all the products?
Yes, there's a function called search landGIS, and you say I'm interested in clay, and it finds all the layers which have clay. So, and you can see exactly how you download the most. So let me see. So I have that somewhere. I'll open a new script for that. Do I have it? Search. No, wait, I'll show you here. So these are these functions. This is, by the way, how you write a package today. Also, RStudio, you have to use ROxygen, and it's all a bit cryptic, but then it compiles automatically and does all the checks. If you want to check a package, you just run here, and it will run the full check whether the package has all the arguments and whether it compiles. So I made this function for the search landGIS. So here, for example, search landGIS, and I want to know clay, and then it will find me the web coverage service layer name. So this is the web coverage service layer name. This is in GeoServer, and this is the actual raw file. And it's on Zenodo, but it's a unique URL. So we have about 400 geotiffs now, and so you don't want to scroll to them. So I made a function search, so it goes and searches by like a key name. If I said I want to search just a clay without depth, so I would just search one thing. Then it finds all the clay for different depths, right? Once you find that it's a web coverage service, then you can do a GDAL operation, like remotely. You don't have to download the 2 gigabytes if you just want one area. If it's more than 500 megabytes, then we block you. because otherwise you suffocate server. So we put a threshold. I think it's fair deal. If you want to download more than 5 megabytes, then you should download 2 gigabytes. But usually you want to download like, I don't know, a few megabytes, and then you use this download land.js.
That's very handy. And it requires another library or shows landmap?
No, it's landmap. It's in landmap, nothing. So it needs to know the URL of the server with the web coverage service. So I'll show you in the after Herod. I will show you one more time landmap, everything you can do with it. It's still a bit under development, so I was hoping that I will be done by summer. But most important, the main idea is there, and I'm getting feedback. So very nice thing about, for example, Twitter today. I put that tweet. So I'll show you. This is the tweet on the. Yeah, this is. So I said I'm working on this package. Yes. So I said I made this package. Here's the code. You want to test it? It got 100. It got a lot of views. 7,000 or something. And then people immediately started writing. So there was a one here, I think. Where's the reply? Here, sorry. Not me reply, I want the reply. Oh yes, so Patrick Schratz, he wrote, you're not using MLR. We are making MLR3. I didn't know. So MLR3 is a scalable machine learning package, and it will run together with the future package. A future package is also for cloud computing. It's very powerful. So he says, we are making the new generation. And now I check the MLR and I say, yeah, everything you have. There's only thing that doesn't work is to calculate the variance of the models. I don't have that in MLR. So I told him, look, I don't have it. Would you like to put that? So now I'm waiting for his reply. And also Ezer, you see, Ezer Pebezma, whose packages, we use he's kind of the backbone of our Spatial. The SP package, RGDAL, the GStat, this is the person. And so he also said, hey, what is this buffer distances? How does it work? So he did ask that, and I said, yeah, go and take a look. This is how you do buffer distances. And so and that's the example we were working on, right? So that was about that. This is just an example. Many people think, okay, maybe we should use this coordinates. Why not use coordinates as a covariate? And I don't recommend it. This is coordinates, right? You will say, okay, well, it's not so bad. You have this blocky structure, but I really don't recommend it. It's maybe if you have like a grid sample or something, if it's a perfect grid, and then use coordinates. But even then, you have again this issue that you're moving outside of the space a lot, and then you will get artifacts. It will be very common. So, do you feel like you would like to use coordinates when you look at these 3 maps, right? Would you use something like this? Would you do it?
If it is more accurate.
It's not, it's not illegal. If you want to use it, when I see this blocky structure or something, and could be that there's some conditions of, like some machine learning that it will have like strange, it will do strange things, or it will be extrapolating in most of the space. No, it's just a projected XY. Dutch azimuthal projection system.
Tom, if you have like the observation in the top north location of your study area,
Yes.
distance to that location is almost like a coordinate, right?
No, because look, that's the difference. When you do just coordinates, it's just two variables. It's just x, y. And when you do buffer distances, each point is a different variable.
That I understand.
Yes.
But you know, if you include the distance to the very top north observation, that's like the y coordinate. And that one.
Yes, it will be. Yes, it will be similar. But it wouldn't be.
That distances are more circular.
Yeah, it wouldn't be perfectly linear. Yes, it will be a bit circular.
You don't like it simply because you have the blocky structure, right?
Well, maybe it's the wrong thing to say that you shouldn't be doing it. I mean, I'm just thinking like there's more sophisticated ways to represent geography, right? So then there's no need to do something which is just mechanical or something. And I think the most sophisticated would be to do this watershed distances, you know, so you really like take into account the distance between points in a watershed or in a so you incorporate some diffusion and deposition processes, right? And then I think, okay, now you're doing something really sophisticated and matches your knowledge, and you know, and then if you have good data, it should pop up. I mean, it should be visible. So, by the way, Harold and me, we had this discussion in the pedometron. We are good friends also, but it was heated discussion in pedometron. It was okay. First, he wrote something. He wrote the time wrong, of course, and then I wrote that. Then I wrote that he's wrong, but I think it was good discussion, and it's kind of like love letters between some scientists. I don't know. It's random forest, yes. Yes, but it's in C++. It's an R package, but everything is C++.
So can you call it ensemble machine learning, like adding other machine learning to it, or all random forest? So like all random forest functionalities were created with like important plus. Can you produce an important plus for it? Like the same thing that we just put random forest? You know what I mean?
Importance, yes. Yes, in Ranger, yes. Oh, you can do, I think, Ranger, absolutely, you want to do random forest in R, use Ranger. Okay? There's these guys from Miami, they also made this random forest SRC. It's also quite, there's extra functionality, and there's this post-model diagnostics is also nice. But it's not maybe for big data. But Ranger, it's like, you know, I do a regression matrix like few million rows with 300 covariates, and it runs in 40 minutes. It's done.
But you also calculate distances?
No, not with. Yeah, so I don't do any more mapping with kriging and stuff. I don't do any of my projects. I now do almost everything ensemble machine learning, but I don't have the distances yet. Not for the serious stuff, because it's very computational, and also I mean, if I have 10,000 points, what do I do? 10,000 maps? I cannot handle that. So when you have classes, let's say you have 6 classes and you have 10,000 points, then you can calculate the distances 2 classes, and then it's only 6 maps. And this thing you can plug in. So you have geography, but it's per class. So you can also do for values, you can do kind of unsupervised classification, and then you get classes for every point, and then you could do distances, and then you reduce number of distances. You don't do for every point, you know, and then you can plug in, and then it's, you know, but ideally, I mean, I would like every point to be included. You know, I like this when you take every point.
But you will be increasing a lot of the prediction time, no? When you are adding.
Yeah, well, everything you increase. If you go beyond the package landmap, if you have more than 1,000 points, I print the warning, don't do it. If it's more than 1,000 points. But if you have 600 points, they show me, yeah, they use the distance to all 600 points. And they say it's the increased accuracy. Where you have a spatial dependent structure. If there's no spatial dependence, or if you explain the spatial dependence with other covariate, then you don't need it. Okay, I think we have to go for the lunch break, right?
Yeah.
So let's stop now, and then Herod will take over. And then after that, we'll do one more session, one more time, Ensemble Machine Learning. So you see, and I'll do the MLR package for you. I'll show you how it works, and I'll show you also this train SP learner, how it works. And you will see that it is very computational, but it's operational. You can use it. Okay, see you after lunch.